Hello everyone. Welcome to the ILTA Physics online problem solving lecture. Today we're going to work through some problems related to torque in rotational motion. Torque is a physical quantity related to the force that causes rotational motion. It's a quantitative measure of how effectively an applied force is transmitted into rotation. As you probably already know, in rotational motion, it's not just the magnitude and direction of the force that matters. The specific location where that force is applied is a crucial factor as well. If you need a refresher on these theoretical concepts, please refer to the previous theory session to make sure you fully understand the material before coming back to these practice problems. I'm sure you already know this, but if you don't truly understand the concepts, your skills won't improve no matter how many problems you solve. Today, we'll look at simple calculation problems for torque and discuss some important things to keep in mind when solving them. We'll also work on problems involving net torque, which occurs when two or more torques act on a single object simultaneously. Now, let's briefly summarize the key concepts related to torque problems. Let's think about the rotational motion of turning a hex bolt with a wrench as shown in the diagram on the right. When the position of the bolt acts as the axis of rotation, the torque applied to the bolt is calculated by multiplying the distance from the axis by the component of the force perpendicular to the radial line, which is connecting the axis to the point where the force is applied. If we calculate this using trigonometry, it can be expressed as Rf sine theta, and the unit is Newton meters. Calculating torque this way is an interpretation from a kinetic perspective, essentially how an applied force causes an object to rotate. However, torque in rotational motion can also be defined from a kinematic perspective using angular acceleration. In other words, it can be calculated as the product of the object's moment of inertia and its angular acceleration. The moment of inertia in rotational motion is determined by the object's shape and the axis of rotation, which we'll cover in more detail in the next chapter. The most typical way to solve torque problems is to calculate torque from both the kinetic and kinematic perspectives for the same motion and then link them together. So please keep that strategy in mind. Another type of torque problem involves relating quantities calculated from torque or force to the object's tangential velocity or angular velocity. I encourage you to practice many problems that ask for the relationship between force and tangential velocity or acceleration, as well as the relationship between torque and angular velocity or angular acceleration. You'll also frequently use the relationship between linear velocity and linear acceleration and angular acceleration. Finally, another type of problem is when multiple torques act on a single object. When several torques are involved, the net torque acting on the object is calculated by taking the vector sum of each torque. By vector sum, I mean you must consider the direction as well as the magnitude. Also, while not directly a torque problem, when force appears in rotational motion from a dynamic perspective, you sometimes need to consider centripetal force and tangential force. To summarize briefly, centripetal force acts toward the axis of rotation to change the direction of the object's motion. Meanwhile, tangential force works to determine the magnitude of the tangential velocity in circular motion. We'll look at more practical questions regarding this in the actual problems later on. Question 24 asks for the minimum force required to hold a door open when the automatic closing torque of the door, which has a specific height, width, thickness, and mass, is 5.2 Newton meters. It might sound a bit complicated, but it's actually a straightforward problem about calculating rotational torque. As explained before, the formula we need is the product of the distance to the axis and the perpendicular component of the applied force. As long as you understand the conditions given and can accurately visualize the rotational motion, it's a simple fix. First, torque in rotational motion is independent of the mass of the rotating object. Also, since torque depends on the distance between the axis of rotation and the point where the force is applied, as shown in the diagram, the height and thickness of the door have no effect on the calculation. Only the width of 0.91 meters matters. To hold a door that closes with a constant torque of 5.2 Newton meters, the minimum force must satisfy two conditions. First, the force must be applied perpendicular to the radial line connecting the axis to the point of application. That is, the angle must be 90 degrees to hold the door with the least amount of force. Second, the distance between the axis and the point of application must be as large as possible to minimize the required force. Therefore, if we plug these into the torque formula, the minimum applied force comes out to 5.7 newtons. The calculation itself is very simple. If you understand the concepts and the problem's conditions, you can solve it easily. Here is another type of torque problem. This one asks us to calculate the net torque when two or more forces act on a rotating object simultaneously. Situations involving multiple forces are given in various ways, either directly or indirectly, depending on the problem. Question 26 describes the motion of twisting a bottle cap with your hand. You might wonder why this counts as multiple forces, but it's because when you grip a bottle cap, your thumb and your other four fingers apply force to two different parts of the cap. You might think it's a bit of a tricky question, but on the other hand, it's a great problem that applies physics to a real-life situation. Anyway, let's calculate the net torque for this case. The diagram shows a bottle cap rotating because forces are applied to the right and left sides. The two forces have the same magnitude but act in opposite directions. As mentioned earlier, when multiple forces are involved, we calculate the net torque by taking the vector sum of the torques produced by each force. In other words, it's the sum of the torques considering both magnitude and direction. Since the magnitudes of the two forces are equal, let's look closely at their directions. For convenience, let's say the force from the thumb, the left force in the diagram, is pointing downward. Meanwhile, the force from the other fingers is pointing upward. From a spatial perspective on a 2D plane, the directions are opposite, up and down. However, the key point of this problem is that from a rotational perspective, both forces cause the cap to rotate counterclockwise around the axis. Therefore, they are acting in the same direction. To emphasize, when calculating torque, you only need to distinguish between clockwise and counterclockwise directions from a rotational standpoint to find the vector sum. This concept applies exactly the same way to determine the direction of rotation in seesaw problems or pulley problems, so please remember it. Once you understand that, the rest is a very simple formula. Each torque is the product of the distance from the axis, the applied force, and the sine of the angle between them. As you can see in the diagram, the force acts perpendicularly, so each torque is simply R times F. Since both forces move in the same counterclockwise direction, the total sum is 2R times F. Therefore, according to the calculation, the value of each individual force is 28.6 newtons. Torque problems are generally simple calculations, so if you understand the concepts and the descriptions well, you'll be able to solve them easily. That's it for today's lecture. Great job, everyone.